Hello everyone, welcome to my video. In this video, we will explore the polar coordinate system. So far, we have looked at the rectangular system xy and normal tangential system nt. The difference between these two are many. One of them is fixed versus unfixed. Most of the time, the nt system is set at the point of interest of where the object is. Polar coordinate system, on the other hand, is same as the xy system. It has a fixed origin. Looking at the example here, one object moving along the path, we can arbitrarily select a fixed point O, establish the system to track the moving object by measuring the distance from O to A, so-called the radius r, and an angle theta measured from the positive x direction. Similar to the xy and nt system, the polar coordinate system also has a pair of unit vectors called er and e theta. Lastly, as I already mentioned, the position vector is given by connecting the origin O to the point of interest. It can be written using unit vector. In this case, little r is the magnitude, and the direction is given by the unit vector er. Same as what we did for NT system, with the position vector ready, we will take derivatives of the displacement r to get velocity. Since the direction is not fixed, so we are ending up with an et dot in the velocity expression, and we need to get this term resolved before we can use the equation. We'll look at an infinitely small time interval again, similar to the situation we were analyzing for the NT system. Due to the small time interval, the change in arc length can be treated as the same as a change in angle, right? Because the change is so small. This gives us der equals to e theta d theta. And this is essentially the arc length equals to the radius, which is the length of the unit vector, times the angle d theta. Since r and theta are perpendicular, when we are looking at the infinite small time interval, the change in r direction is related to theta and vice versa. If you look at this diagram on the right-hand side, I make a right angle here. This is essentially, this is r, right? This is measuring our r direction, and the theta is perpendicular, measuring from here. So usually theta is here, but I move them to make them perpendicular. So this is essentially like I am rotating a little bit. So the ER rotate a little bit, and E theta also rotate a little bit, right? Thinking about this. Either like this or like this. This is theta, this is R. So now it's time to rearrange. We will do so by dividing each side with the dt to get the time derivative. And then we have obtained the time derivative of both unit vectors, E theta dot and ER dot. Given that what we obtained on the previous slide, plus the velocity we had at the very beginning, we'll sub in everything, and we get our velocity equation for the polar system. We can also use its scalar form from time to time, occasionally when it's convenient, when the scenario is suitable. So the scalar expression gives us Vr equals to r dot, and V theta is r theta dot, and the overall velocity is given by the Pythagorean theorem, Vr squared plus V theta squared under the square root. With acceleration, it's pretty much the same thing as we did for velocity. So I'm not going to repeat much here. Here we'll have the acceleration equation that you can use for the polar coordinate system, and just showing on the screen. Take a screenshot and write it down. Let me put everything together here that we have obtained so far. For polar coordinates, there will always be a velocity and acceleration to consider. And for each variable, you always need to consider the r direction and theta direction, right? The r theta system. Given the generic relation above, we have obtained these relations for velocity and acceleration. These are scalar forms, and these are in vector form. Okay, please pay attention to the scalar times vector combination, the vector product combination in this expression. It's a vector and scalar multiplied together. In the NT system, towards the end, we looked at the circular motion, which was a special case. Well, circular motion is still a special case for the polar coordinate system. When we are using the center of the circle as the origin for the polar coordinates, the equation can be simplified a lot. But this only works when the origin is at the circular motion center. For example, in this case, the origin is not at the center of the circle, the origin is O and the center is at C. Then these simplified equations cannot be used. We will have to use the generic equations we derived on the previous page to treat this type of equation. So be careful. You can use simplified polar coordinate system equations for circular motion only when only when origin is set at the center of the circle. Here's a list of the sample problems you should review. Thanks for watching. I'll see you next time.